Hello, I'm Jose Peñaranda, and I'll be presenting to you the latest results on our research Laniakea supercluster in a cosmological context. This presentation has two main objectives: to review the topics presented in the last presentation about this topic on the seminar, and to present the new research results. But first, a short summary of the previous presentation. We are conducting a study on Laniakea, a supercluster defined by Tully in 2014 through the application of a Wiener filter on cosmic flows to data. This research pretends to use embodied simulations of public domain from the Abacus Cosmos project and a watershed algorithm with the purpose of finding structures in the simulations that will be compared to Laniakea. We were focused on three different measures for Laniakea: density, volume, and mass. However, we will focus only on volume this time. We use a watershed algorithm on the velocity divergence field to find the superclusters. The algorithm segments the whole volume by assigning each voxel to a unique supercluster. The figures on this slide present a watershed algorithm process. Initially, we have a set of points with different values of a specific measure assigned. In our case, that is the divergence. This algorithm starts assigning each point a specific group according to its divergence value, and finishes by segmenting this set of points in the groups shown in the figure on the bottom. We interpolate the peculiar velocities for all halos on a grid using a clouding cell scheme. We use a cubic grid with 360 cube voxels, which means that each voxel is a cube of 2 megaparsecs by h on a side. After the interpolation, we smooth the velocity field using a Gaussian filter of physical scale sigma s. We compute the velocity divergence on this smooth velocity field. And finally, the velocity field and the divergence field are expected to have a significant dependence on the value of sigma s. In order to quantify this influence, we use values of 2, 6, 10, 14, and 20 to measure the impact on the velocity and divergence distributions. Figure on the left shows the velocity norm distribution for 4 different values of sigma s. As this value is increased, the distribution becomes more symmetric, while the width of the distribution is reduced. The smoothing brings the data closer to the field average. These changes are also present in the figure on the right, where we have the same kind of analysis, this time for the velocity divergence. It is also observed that the range of divergence values gets reduced when sigma s increases. In addition, this figure evaluates the effect of the Gaussian smoothing parameter on the standard deviation of the divergence field. As expected, according to the idea of data coming together to the mean value, the standard deviation decreases as sigma s increases, which implies the higher the value of this parameter, the closer data gets. Finally, the influence of sigma s on deciding of structure formation must be analyzed. These effects can be seen in this figure, where the same cross-section of the divergence field is shown but smoothed with sigma s equals 2 and sigma s equals 10. These plots show a random section of the divergence grid with size 300 megaparsecs by h squared. With small sigma s, many structures are visible in a fine network in the divergence grid, while large sigma s differentiates big structures of high aggression with barely any resolution of smaller filaments. Also, using large sigma s causes big values of divergence to be smoothed and values of the field move closer to the average value of the field. Since watershed algorithm takes the divergence field and segments it into disjoint groups, in this case superclusters, it is expected that sigma s also modifies the result of the algorithm by transitivity. We mentioned that increasing the Gaussian length causes big values of negative divergence to become large structures with negative divergence. Therefore, since the algorithm classifies according to the behavior of these structures. If they get bigger, superclusters detected by the algorithm will become greater too. As a result, a drop on the number of superclusters detected must be observed. The behavior of the number of superclusters found as a function of sigma s is shown in the figure. Indeed, we observe a considerable reduction of the number of superclusters found when sigma s is raised. As mentioned before, this figure shows a random section of size 300 megaparsecs by h squared of the divergence grid using sigma s equals 2 and 10. Moreover, this figure also presents the groups found by the algorithm corresponding to this section, with a circle of the same diameter of Laniakea in the middle of each chart. First, it can be seen that there is a clear correspondence between the state of the divergence grid and the structures found. It can be seen that even when the value of sigma s is raised from 2 to 10, superclusters detected by watershed method are much smaller than the reported size of Laniakea. The behavior of the volume distribution of the superclusters for different sigma s values is presented in this figure, where the same simulation is smoothed using sigma s equals 2, 6, 14, and 20. In addition, a vertical line is drawn to mark the reference of the volume of Laniakea. We can see that we have to go to high values of the Gaussian length if we want to make Laniakea a typical supercluster. From now on, the value reported by Tully in 2014 in his studies on cosmic flows to data is used. Thus, the value of the Gaussian length is fixed and equals 10 megaparsecs by h. In order to complete the analysis of Laniakea, it is important to establish a pattern by using different sets of simulations. We are interested in the impact that different cosmological parameters may have in the volume distribution of superclusters, as well as the behavior of this distribution when different time evolutions are considered. First, we consider simulations using 2015 Planck cosmological parameters. Therefore, a set of 5 simulations of the Abacus Cosmos 720 box Planck catalog is considered. This set of simulations fulfills two main functions. First, it allows us to observe the effects of the time evolution on the resulting volume parameters. We are able to establish a reference point with generally accepted cosmological parameters. This figure shows the volume distributions of superclusters found by the watershed algorithm using this dataset. This chart also shows a vertical line where the reported volume of Laniakea is located. As expected from the previous analysis on sigma s influence, Laniakea is larger than any other simulation found by the algorithm, and it does not change with different time evolution. Now, we consider extreme values of cosmological parameters. A set of 4 simulations of the Abacus Cosmos 720 box catalog, as well as an Abacus Cosmos 720 box Planck reference simulation is studied. From Abacus Cosmos 720 box, we extract the 4 simulations that correspond to the highest and lowest values of omega n and sigma 8 found in this catalog. The resulting volume distributions for this dataset are shown in this figure. A vertical line representing the volume of Laniakea is shown too. We observe that even when extreme cosmologies are considered, the volume of Laniakea is located outside the distributions, and therefore this supercluster conserves its atypical size and behavior. First, we conclude that the use of watershed algorithm is appropriate for delimiting superclusters in simulations. Second, although the value sigma s has a great influence on the volume distributions, for values close to those corresponding to previous Laniakea investigations, it is true that this supercluster has an atypical behavior. And finally, it was observed that even when extreme values of cosmological parameters were used, the volume of Laniakea was found to be much bigger than any other supercluster found in the simulation.